Hello everyone, in this video we'll discuss about the force vibrations due to rotating masses. Now we already know that in all types of rotating machineries, maybe electric motor or turbine or a pump, they always consist of some unbalances. And why these unbalances are there? They are because of the rotating masses in the body. We have already discussed about the balancing of the rotating masses in another chapter. And these unbalances which are left in the rotating bodies, what they do, they produce the vibrations in the system. So we have assumed that there is a machine, right? And it is mounted on a floor, right? The fixed floor is there and it is attached to a spring and a damper. And whatever are the unbalances in the machine, we are representing them with the help of a small mass which is m, and this mass is at a distance e, which is also called as eccentricity from the axis of rotation. And if we assume that the total mass of the machine is capital M, so basically this M is the total mass that will vibrate because of the unbalance produced because of the this small mass that we are considering M. So because this is a rotating system, so what will happen? This M will produce a centrifugal force, which is actually the unbalanced force in radially outward direction, right? So this is how it will rotate, right? It will rotate like this. So at various positions, the value of this angle theta will keep on changing. So if we assume that at any instant this rotating mass is at angle theta, right, with the axis of rotation, and this is the centrifugal force. So this centrifugal force will have two components. One, a vertical component which is me omega square sine theta, and a horizontal component me omega square cos theta. Now what will happen because of these unbalances? The system will vibrate in vertical direction as well as in the horizontal direction, right? So it will basically depend upon the value of sine theta. So there will be two types of vibrations produced in the system, vertical and the horizontal systems. But here we are considering only the vertical vibrations. We will not take into account the horizontal vibrations produced because of these rotating unbalanced masses. Now, if we draw the free body diagram of this mass M, so it has the spring force, which is the spring constant into displacement. So what is happening? Because of this unbalanced mass, if initially this machine is at some position, it will be displaced by some distance in the vertical direction, right? So let this displacement be x, right? So let's say if the axis comes to this position, a new position is there. So this distance is denoted by what? X. And the damping force will be c into, that is damping coefficient, into x dot, that is the velocity, right? And what is happening? We are assuming the condition when the body is moving in the upward direction, right? And the direction of centrifugal force, right? Because this centrifugal force is producing a vertical component that is producing the vibration in the system. So the force we have, it is me omega square sine theta, right? So the motion of the body because of these forces will take place in this direction, or we can also say that there will be inertia force acting in the direction opposite to that of this centrifugal force, the component of centrifugal force which tries to move this mass in the upward direction. So if we apply the D'Alembert's principle, we can say that the inertia force, the spring force and the damping force, it is equal to this harmonic force produced because of this unbalanced rotating mass. So the equation becomes like this, which is mx double dot plus c, that is into x dot, that is the damping force, plus the spring force is equal to the harmonic force, which is me omega square sine theta. Now what we have to do, if you look at this equation is similar to that of the equation that we have already discussed while doing the forced vibrations for damped system. There the force applied was F naught uh, sin omega t or cos omega t, right? So what exactly is changing? If the force, let's assume that F naught sine omega t is acting on the system, so you can understand that whatever the equation of amplitude we found initially, only the value of F naught will change. So instead of F naught, the force that will be applied will be me omega square. So we'll do a simple analysis to just understand how to find the value of the amplitude, right? So let's assume a lump parameter system with mass m attached to a spring of spring constant s and a damper, right? And this is the direction of displacement of this mass, and if some harmonic force F naught cos omega t is acting on the mass in this direction, so the free body diagram will look like this, right? The harmonic force is acting in this direction, so the spring force and the damping force will act in the opposite direction, and inertia force will also act opposite to the direction of the harmonic force. So if we write the equation, it will be like mx double dot plus cx dot plus s into x is equal to F naught cos omega t. Now, if I want to find the value of the displacement, which is a function of time, it will be x cos omega t if there is no phase lag. But if there is some phase difference, we write the equation as x cos omega t minus phi. So from where are we getting this equation? So let's take a simple example. Now see what we are saying the displacement is x cos omega t. Why we are saying this? Because if there is some displacement x, right, at some angle omega t from this, let's say the projection time or the horizontal axis. So if this is x, what will we get? The component along this projection t, it will be x cos omega t, right? So in this way, we can draw the diagram for all the forces, for all the components that are acting on this mass m. So if x is x cos omega t, what will be its velocity? It will be minus omega x sine omega t, and if you apply the trigonometric relations, we can write this equation like this, which is omega x cos omega t plus pi by 2. So if I plot the diagram, if x is at angle omega t with the projection t, so omega x will be what? That means the velocity, right? It will be at this angle, which is omega t plus pi by 2. So if this omega x is the velocity, if you want to find the component along this axis, it will be omega x cos omega t plus pi. So this is what the value is telling about, right? Similarly, its acceleration will be minus omega square x cos omega t, and this can be written as cos omega t plus pi. So the acceleration, the maximum value of acceleration, which is omega square x, it has an angle of omega t plus pi, right? So by using these general equations, we can find whatever components we want to find. But here we are taking the maximum values. So if I plot all these three components, so along the displacement x, what is the force that is acting? It is the spring force. So we'll draw Sx in this direction, right? Then we'll add to this what? The damping force, which is omega into x. That is the velocity component. So it will be omega c omega x, right? Then we'll add the inertia force to this, which is m in mass into acceleration, which is m omega square x, because we are considering that the body is rotating at some angular velocity omega, right? So this is rotating body. So m omega square x, which is perpendicular to c omega x. Now if we apply the D'Alembert's principle, we say that if the system is in equilibrium, the summation of all the forces should be equal to 0. That means this should be a perfect, a complete vector diagram, and this F naught will give the resultant force. So if I make a small construction from this point, if we draw a line perpendicular on Sx, right? So can we find the value of F naught? So in this triangle, let this be A, B, and C. And if we are saying that this angle C is 90 degrees, so we have made a right angle triangle. So F naught square, applying the Pythagoras theorem, will be equal to this distance. This distance is what? Sx minus m omega square x whole square plus this. So this is equal to this value. So it will become c omega x square, right? So from here we can find the value of x, that is the amplitude of the system, which is f naught upon s minus m omega square under root of s minus m omega square whole square plus c omega square, right? And we can change this omega square, right? We take like s common, and so it will be like this, f naught upon s, and we can change this m omega square and c omega square in terms of the damping coefficient, which is zeta, and the frequency ratio, which is omega upon omega n, right? So this is the value of amplitude that we have already discussed about. Similarly, we can also find the phase angle phi for this system. So phi is what? It is sine upon cos. So it will be this factor upon 2 zeta omega upon omega n upon this factor, which is 1 minus omega upon omega n square. So coming back to our problem, we have already discussed that what is the equation that we get. The amplitude, we have discussed that this is the amplitude for any system. But in this case, F naught is replaced by the force, which is me omega square. Now this me omega square upon s, we can write, if I multiply and divide m, which is the mass of this machine, into the equation, it won't make any difference. So can we write this term in this way, which is me upon m omega upon omega n square, right? And in this equation, if I take this term me upon m on LHS, so equation looks like this, which is a upon mass of the rotating body into eccentricity upon the mass of the machine will be equal to this factor. So this equation provides what? The steady state amplitude, and this amplitude is what? It is a function of the damping factor, which is zeta, and this zeta, and the frequency ratio, which is omega upon omega n. Now if we plot a graph between this factor, which is a upon me upon m, and on this hand on x-axis we have omega upon omega n, which is the frequency ratio. So this is the kind of plot that we see, and in this graph we can see that at higher values of the frequency, so the values are increasing. So this is 1, right? So values are increasing in this direction. So we can see that as the frequency ratio values are increasing, its amplitude is also reducing, and amplitude can be reduced by reducing what? If I want to reduce this value, we can reduce mass and eccentricity of the rotating balance. So for such systems, usually higher frequency ratios are preferred. Now we know that what the rotating masses are creating the unbalances in the both vertical and horizontal directions, but the reciprocating masses, they also produced unbalances in the system. So here we have made a small diagram. We have already discussed about the rotating and reciprocating masses. So which is the mass of this piston cylinder, right? So if let's say the whole machine has got this system, and because of this reciprocating body, which is the piston cylinder, if there is some unbalanced, how do we balance it? So we know, we have already discussed this, that the inertia force of the reciprocating masses or a reciprocating body is given by this formula, which is mr omega square cos theta. Theta is the angle which the crank makes with the line of action, plus cos 2 theta upon L upon R, where L is the length of connecting rod and R is the length of the crank. So usually in cases what happens, that this L upon R is very large. So if this L upon R is very large, this factor becomes quite small. So we can ignore this harmonic function, and what we take further is this equation, which is mr omega square cos theta. And if we are only considering this factor, and if you draw the free body diagram of this mass, it will have what? The damping force and the spring force, the damping force, right, and this harmonic force, which is mr omega square cos theta, and the inertia force. So this is how the equation will look like, and this is exactly similar to the equation that we have already discussed. So the amplitude, the and all the values, they remain same. So similarly we can analyze any rotating or reciprocating masses unbalanced in any system.